All right. Well, I have to start, of course, by thanking George for the invitation and organizing the conference so many times. Always have a great time when I show up here. And I'll also mention that this is joint work with Pierre-Colin Dufresne, who's a professor of finance at EPFL. So the nature of the subject we're going to be studying here is related to the Kyle model. So I'm going to give a very brief outline of what the Kyle model is in case you happen to not be familiar with it. And then I'm going to talk about the additional features that we're adding and why we're interested in these new features. The Kyle model is, it proposes a market with three distinct types of traders or agents: a market maker, a profit maximizing insider, and a liquidity trader. The ones marked in red and blue, the market maker and the insider, are strategic traders. They're actually accomplishing some kind of objective. In particular, the insider has some kind of knowledge of a future value of an asset, and they're going to try and exploit this knowledge to maximize expected profits. At the same time, the market maker is trying to set the transaction prices of transactions in a competitive manner. Essentially, the market maker is trying to sniff out the information that the insider has. And he's going to use that sniffing out to set the price of the transaction accordingly. So in the original paper in 1985, Kyle defines a notion of equilibrium in this setting, studies the equilibrium, and the main takeaways are: how do prices change over time to reflect information being encoded into the market? The sequence of events which occur in the Kyle model are kind of fundamental in terms of understanding what's going on. I'm going to repeat this exact slide in a few minutes, except I'm going to highlight the new features that we add so you can really see. You have to understand the original Kyle model to see where the additional features come in. So it really is just a sequence of steps of things that happen. Initially, the insider receives some kind of signal, which we'll call V tilde. V tilde is actually going to represent the liquidation value of the asset in the future. But the key point is that this is revealed only to the insider. The market maker can't actually see V tilde, but the market maker does know that it has some kind of distribution. Then the insider submits an order of size delta X. This order is submitted to the market maker. Simultaneously, the liquidity trader submits a size of order delta Z, which is a random variable completely independent of everything else in the model. The market maker observes the total order flow, which we're going to call delta Y. So the market maker does not observe delta X or delta Z independently. They only observe the combination. Then the market maker sets the price of the trade, P1. Okay, so of course, the insider himself spends P1 times delta X. And then after the insider has acquired this position, they liquidate their position, and so they earn a value of V tilde times delta X. Okay. In terms of the strategic behavior that these two agents are undergoing, I mean, I've outlined the dynamics of what's happening. But as I've mentioned already, the insider is trying to maximize expected profits because they have this additional information. So they're just maximizing the change in wealth that they have. Of course, they spend some amount, P times delta X, and then they earn some amount, V tilde times delta X. But they're allowed to condition on V tilde, right? This is the signal that has been revealed to the insider before any of the trading actually occurs. The market maker is trying to set the price according to the future expected value of what the asset is. But the information that the market maker has is different than the information that the insider has, okay? So we're allowed to condition on delta Y because that's the variable that they actually observe. As is typical in some kind of game theoretic setup, both agents are taking into account the strategic behavior of other agents. This leads us to a very natural notion of equilibrium. And in the original Kyle paper, the unique linear equilibrium is classified by these two linear strategies. In particular, the trade size is linear with respect to the initial mispricing, and the change in price is linear with respect to the net order flow. Okay, there's a huge number of extensions of Kyle's model. I've only highlighted a few here that are somewhat similar in spirit to what we're going to be doing. I'm not going to go into too much detail of these, but we can talk afterwards if you want more details. The main sort of common elements amongst all of these are we don't necessarily have a risk-neutral insider anymore. We have risk aversion. And in some sense, the signal is not necessarily perfect. So the two new features that we're going to be studying this are residual risk and activism. By activism, what we mean is that the insider is able to expend some kind of effort, which comes at a cost, so that they can actually explicitly change the liquidation value of the asset in the future. Residual risk, what we mean by this is that the insider receives an imperfect signal. So they don't have an exact value of what the future liquidation value is. There's some kind of additional error term. So throughout the rest of the work, we're going to replace the liquidation value with three terms. The variable v represents the signal that the insider gets. The variable w, this is actually going to be a choice variable of the insider. This represents the amount of effort that they expend so that they can change the fundamental value of the asset in the future. And epsilon is going to be independent of absolutely everything to add a little bit of residual noise into the liquidation value. Okay? So think about an agent or a firm that has an extremely large position in a company to where they can actually dictate management of the company. Okay? So in addition to these additional dynamic terms, we're also going to allow the insider to have a utility function. We're going to use Kara utility for tractability reasons. And there's no reason to consider this residual risk term, epsilon, without having some kind of utility function, because if they were risk neutral, this epsilon wouldn't matter at all. Okay, now why are we considering these two additional features? Well, it should be pretty clear why an imperfect signal is important. In the original Kyle paper, one of the strongest assumptions made is that the insider has exact information about what the future value of an asset is. Very strong assumption, okay? On the other hand, activism is something which has been very heavily studied in recent times, both at a theoretical and an empirical level. Some examples of work done in this. The first 2 points here, these highlight some papers that study different equilibrium models that incorporate shareholder activism of some type. The bottom 2 points here do a lot of empirical studies on the sequences of trades around agents that are identified as activists. So there's some regulation by the SEC that dictates if you become a large enough shareholder in a firm, you have to actually reveal, one, that you are a large shareholder, and two, you have to identify all of your trades for the previous 60 days. Okay, so this basically creates a data set, and you can start to study some empirical features of activism. Okay, so this is a slide that I had a couple minutes ago. It's exactly the same. Can you see that some things are in green? Yeah, okay, so the green sticks out. All the green terms are the new ones that represent things that we've added to the standard Kyle model. So in particular, the insider receives a signal V, but also an initial inventory which is random. Well, it doesn't have to be random, okay? So V and X are bivariate Gaussian vector. The variance of X could be set to 0. Everything kind of still works out here. But again, it's a key that this is revealed only to the insider. The next few steps are identical to the standard Kyle model. So the insider and the liquidity trader submit a trade simultaneously. Then the market maker sets the price. But the market maker also has to estimate what the insider's inventory is going to be through time, okay? And I'm going to emphasize in the next slide or so why they have to keep track of what they think the insider's inventory is going to be, okay? After the trades have been submitted, the insider is then able to select the effort level that they expend, and this is going to come at some cost, which we'll denote by C. And so the final terminal wealth of the insider is represented by this expression at the bottom, okay? So we have the liquidation value of the asset. This is the three terms that we added up before, multiplied by the net position of the insider. We subtract the price of the trade, or the total cost of the trade to the insider, and we subtract the cost of the effort. Okay? So how do these things all kind of interact when we actually put everything into the utility function? Well, it's pretty... Let me introduce a little bit of a notation first, okay? For tractability reasons, we're going to consider a quadratic cost to this effort, parameterized by this parameter psi. From now on, I'm just going to call psi activism. If psi is very large, this means the cost is small, and the shareholder has a very strong sense of activism, okay? So large psi means large activism. I'm also going to be calling alpha residual risk, okay? So it's the risk aversion parameter of the insider multiplied by the variance of this additional noise term, okay? So alpha represents the total risk incorporated into this epsilon. At the end of the trading, it's very straightforward to show that the optimal effort expended by the insider is just psi times their terminal inventory. So from now on, we're always going to assume that the effort is psi times x. And then if we integrate out the residual risk in the utility function, the new performance criterion of the insider is the following. I've written it in this form so you can see this is kind of like the standard term which comes up in the Kyle model. But we have an additional influence of inventory. And we see that the activism and the residual risk are counteracting each other correspondingly, okay? The objective of the market maker is also slightly different. They're not just trying to sniff out what the signal of the insider is, but to set the price competitively, they're trying to figure out the signal plus the effort level of the activist. Okay. So on this slide, I'm explaining why the insider has to, or why the market maker has to try and estimate the inventory level of the insider. So in the standard Kyle model and in many different generalizations of the Kyle model, you have that the optimal trade size is going to be linear in the mispricing or in the signal, the difference between the signal and the expected signal. But the performance criteria on the previous slide has an explicit inventory dependence, right? We have this quadratic value in terminal inventory. And so you should expect that there's going to be a component of the optimal trade size which depends on the inventory of the insider. But if the trade submitted to the market maker depends on my inventory, then the market maker should probably try and figure out what my inventory is as well, okay? So by Q, I'm denoting the market maker's estimation of what the insider's inventory is, okay? But then if you think to yourself, if the market maker is trying to estimate what the insider's inventory is, then the insider should probably base their trade also on what the market maker's estimation of my inventory is. So we kind of keep going back and forth on adding more state variables and dependence and stuff. But once we add this, we've come full circle. There's no more things to add, okay? So the dimensionality of the problem has gone up from 2 to 5 in some sense in terms of the number of variables we have to keep track of. We're going to restrict ourselves to recursive linear strategies. So in particular, we want all of the strategic behavior to be based linearly off of the underlying variables. This form of the problem it's tractable but not complicated, okay? And the general idea here is that if I give you the 3 constants which dictate the trading strategy, then standard Gaussian projection theorem or the Kalman filter give 3 constants which determine the pricing rule. And vice versa. If I give you the 3 constants which determine the pricing rule, they appear all over the place here, then a standard optimization gives as an output the 3 constants which give the trading rule, okay? So natural form of equilibrium, we're looking for a fixed point to these 2 maps. So the first theorem, at least for the single auction case, is that equilibrium is characterized by any positive root to this 5th degree polynomial. So this is a pretty big, messy expression. Doesn't really lend to analysis too much, but we can say a couple of things. So if I find a positive root to this polynomial, then all the other 5 constants that are relevant, we have in closed form. In addition, we have 3 conditions which guarantee that the positive root of this polynomial is unique. The one that I really want to highlight is this first one. Remember that alpha is this residual risk. If alpha is 0, everything is nice, we have uniqueness. If alpha is non-zero, we don't necessarily know if we have uniqueness. The first question you might ask is, do you have examples of non-uniqueness? Yes. So this is a nice example where the optimal response curves intersect in only one point. Okay? The blue curve represents lambda as a function of beta. The red curve represents beta as a function of lambda. Fixed point, find all the other constants, we're happy. If we change the parameters around a little bit, we have non-uniqueness of this one auction equilibrium. To the best of my knowledge, this is the only Kyle-type model that has a non-unique equilibrium. And we don't actually know a good way to explain this or to resolve it. You might say to yourself, there must be a way of choosing one of these 3 points in the most reasonable way. But the problem is that if you vary the parameters continuously, what happens to the roots of these polynomials? Well, they move around continuously, right? But they move around continuously in the complex plane. And what happens is sometimes 2 roots will kind of come and meet, and then you go from 1 equilibrium and you jump up to 3. And then you move the parameters even more, and the roots go from 3 down to 1. But the one root that stays is not the same one. So even if you choose one of the 3 roots in a reasonable way, that equilibrium will not continuously depend on the underlying parameters. Okay? So don't have a great explanation for how to interpret this, but it just comes out of the mathematics. Now, I haven't talked at all about the multiple auction case, but it's very simple to generalize the problem to multiple auctions. And in the next 2 slides, I just want to illustrate again that this residual risk term is the one that actually causes a lot of problems. So what I've done here is I've solved numerically for a 400 auction equilibrium when the residual risk is 0. And you'll notice that 2 of these plots give me quantities which are identically 0, okay? What am I plotting here? I'm plotting, no longer am I plotting 6 constants, I'm plotting 6 sequences, because we now have a trading strategy and pricing rule which change through time, and they depend on 6 different sequences. But when residual risk is 0, 2 of these sequences are identically 0. When I turn residual risk on, we have something really messed up happening here. Okay? We're going to move to the continuous time version in a minute, but in a lot of these Kyle models, very often you kind of make a prediction or an educated guess on what the form of the equilibrium is going to look like. What is a good guess? Well, look at the discrete time version. Okay? What is this supposed to represent in terms of a continuous time process? Okay? It's not really clear. Is it actually identically 0 for this whole time? Does it oscillate wildly at the end? I don't really know. Well, I do know in the continuous time version, okay? So we do have some answers. Okay. I'll go through this slide fairly quickly because this is exactly the natural continuous time generalization of what we did in the single auction case. So once again, the insider chooses their optimal level of effort depending on their terminal inventory. We are going to make a restriction that the insider trades absolutely continuously. So in most versions of the Kyle model, there's no restriction on the form of the inventory process. They can have diffusion components. They can have jumps. However, it can be shown that in equilibrium, almost always, in most versions I know of, it is suboptimal if you do not trade absolutely continuously. So we're just going to make this assumption right from the bat. We probably don't lose much generality. What it does help us to do is we can make some manipulations of the terminal wealth in the future, which are convenient. Okay? The new optimization that the insider is trying to solve, well, again, this is just the continuous time generalization of what we saw in the single auction case. In particular, this term here is the total cost of trading through time. Okay? That kind of takes the place of P times delta X. The objective of the market maker now, again, is to try and estimate the terminal liquidation value based off of the sequence of observed trades, which is the net order flow. Okay? For the remainder of this talk, I'm actually going to set activism to 0. Now, why am I doing this? There's a lot of moving parts are going to come up. A lot of the expressions are already not very tractable. There's a lot of things going on that you have to kind of keep in your head. We can do everything here when the activism is positive. I do have some comments about the differences in the equilibrium that we classify, but for the most part, everything works identically if psi is positive, but a lot of the expressions, which are already messy, are a little bit simpler when we just set this parameter to 0. Okay? And the way that I'm going to structure the rest of this is what you would probably do in any kind of two-player game theoretic setup. You fix the strategy of one agent and solve the problem for the other. And then you flip and you look for some kind of fixed point. A lot of the people that I've discussed these types of microstructure problems with, they just jump straight into equilibrium somehow. They must be a lot smarter than me. I really need to think about both sides of the problem individually. Okay? And of course, because of the nature of the objectives of the two agents, the market maker is solving a forward-in-time problem, and the insider is solving a backward-in-time problem, right? One of them is Gaussian filtering, and one of them is stochastic optimization. Okay? Once we go through both sides of this problem, we're basically going to derive a large set of necessary conditions we need to be satisfied, and we're going to try and find how we can satisfy all of them at the same time, and that's what I mean by filling in some missing bits. Okay? We're also going to make one major simplification to this. So the insider's objective when the activism is 0 is what's written on the first expression here. Pretty straightforward optimization problem. We're going to replace it with an alternative optimization problem. So basically, all I've done is I've gotten rid of this exponential. And why is this probably a reasonable thing to do? Well, the residual risk, the epsilon term, has already been integrated out, and it's accounted for here. Okay? So as long as this alpha term is positive, residual risk is still present in the problem. The only thing we're kind of lacking is we no longer have risk aversion towards the Brownian motion. The only two random components in this problem, in this expression here, the only randomness is coming from the Brownian motion of the noise traders and the residual risk term epsilon. By integrating out the residual risk and then sort of dialing back down to a risk-neutral version, we're basically still risk-averse towards epsilon, but we're now behaving in a risk-neutral manner towards the noise traders. This is a huge simplification in terms of tractability. We have a huge number of problems if we don't make this change. Okay? We basically can't make any progress if we don't make this change. One more simplification, and this is where it's useful to have the absolutely continuous trading strategies. We can do an integration by parts on the terminal wealth, and we can basically write the entire objective in terms of this one quantity that I've highlighted in red. So from now on, this I'm going to denote by zeta. Okay? If the objective of the insider only depends on zeta, right? It doesn't depend on p or x individually. It only depends on some linear combination. This is just going to give us a dimensional reduction. Okay? V and Q are going to represent the two quantities that the market maker is trying to estimate through time. So namely the signal and the inventory of the insider. Okay, this is the first part of this divide and conquer. So what we're doing is we're going to fix the insider's strategy. Okay, so the functions beta, gamma, and eta are completely arbitrary. I don't care what they are. Our insider is not acting in any intelligent way. But given beta, gamma, and eta, what are the correct pricing rule and inventory estimation rule? This is just continuous time Gaussian filtering. There's a lot of formulas here, but the mathematics isn't really complicated. Some interesting things to look for, though. The price will still be a martingale, even though it doesn't really necessarily look like one. If you look at the assumed version of the trading strategy, there's this component which does not have an expectation of 0 in the market maker's filtration. Okay? But that component is subtracted off of the net order flow before being fed through into some price impact. And so the price will still be a martingale in the market maker's filtration. Another pretty interesting thing to look at, if the signal and the inventory, the initial signal and inventory, remember those are a two-dimensional Gaussian vector. If they're independent, as soon as trading starts, then in the market maker's filtration, they're no longer independent. They'll actually be correlated. Okay? And you can see that directly from here. Sorry, not there, this one. Okay? So the covariance between x and v changes over time. If it starts at 0, it may become non-zero. Okay, so this is why we needed this huge simplification. This is the other side of the divide and conquer. What we're going to do, in some sense, is fix the pricing rule and the inventory estimation rule and try and figure out what the optimal trading strategy is going to be. So this is a huge mess. I think the way I should have written this slide is I should have started down here. Okay? So assume that the pricing rule and the inventory estimation rule take this form for arbitrary lambda, cap lambda, and eta. Okay? Then we define, basically what we do is we define these quantities, and we in fact have this restriction. We need lambda and cap lambda to be related to these functions k1, k2, k3. Now, where does this actually come from? If you studied continuous time Kyle stuff ever, if you take an HJB approach, well, you just kind of plug the pricing rule into the HJB equation, and you actually end up, as an output, you get a restriction on the pricing rule. You cannot have arbitrary pricing rules because then a value function won't exist, and you have some kind of trivial behavior. Now, this restriction usually takes the form of an ODE on the price impact function lambda. In our case, with the expanded dimensionality, the restriction is a system of ODEs, a three-dimensional system of ODEs, and a two-dimensional algebraic system of equations. This is the solution to that three-dimensional ODE and two-dimensional algebraic system. Okay? So if these restrictions are satisfied, then we have the value function of the insider. It's quadratic in the state variables. And any strategy which forces this to 0 at time capital T is optimal. And this is kind of the nice generalization from the standard Kyle model, where any strategy is optimal as long as it's absolutely continuous and forces the price towards the signal. Okay, now we do have a problem. We've done the divide and conquer. We've set up one agent's behavior and solved what the other agent is trying to do, and vice versa. But there's something missing. And it has to do with this function eta. So for an arbitrary function eta, the filtering can be done, very straightforward. On the other hand, for an arbitrary function eta, the optimization can be done. But this means that eta is not specified, right? We chose eta arbitrarily for player 1, and then we chose eta arbitrarily for player 2. It doesn't give us as an output what this function eta is. Recall that eta is the loading on Q in the trading strategy. So the resolution to this is going to come from identifying a consistency condition. Remember, we have a forward-backward problem, right? So we need to look for something which can be computed using both forward and backward dynamics, and we better get the same thing. So the way we do this, you know what? I'm going to skip this, most of this. Ignore the top half of this slide. Let's just focus on the bottom half. The correct consistency condition is what's written here. And the reason I'm calling this the consistency condition is because the terms on the left and the terms on the right can both be computed using either the forward version of the problem or the backward version of the problem. And we have to find a function eta which gives us the same thing, in both directions. So the question is, can we do this? Well, it turns out we can, but only if alpha is greater than psi. This is another thing we can't really explain in terms of the general properties of equilibrium. So I've set psi equal to 0 in all the expressions I have previously. But like I said, we can do everything with non-zero psi. But this step completely breaks down if alpha is less than or equal to psi. And we don't really know why. Now, we have some properties of the solution to this consistency condition. There are, in fact, an infinite number of functions eta which allow it to be satisfied. and they're parameterized by a single positive constant. They all have the property that they go to negative infinity at the end of the horizon, but they integrate to something finite. Now, the fact that there are an infinite number of these functions is actually a good thing. This introduces an additional free parameter, a degree of freedom. So the full classification of equilibrium, we have 3 degrees of freedom, some B, which determines the value function, C, which determines a solution to some crazy ODE, and any choice of this terminal variance on inventory. Now, how do we get equilibrium from this? We have an ordinary differential equation. It's not a rational function here. These things are all a mess. But we can prove that there's a unique solution which satisfies all the integrability requirements that we need. And then everything just comes out in closed form from this. The problem is that this is such a strange and complicated classification of equilibrium that, I mean, tractability is completely gone. And it's very difficult to interpret what a lot of these terms mean. I'll give, say, one interesting property of what the equilibrium is, because I'm being shouted at. The signal of the insider never gets fully revealed. Okay, so at the end of trading, the signal of the insider in the standard Kyle model usually becomes known by the market maker. But there's a residual variance in the signal of the insider, so their information is not revealed. However, the correlation between the signal and the inventory gets forced to 1. So what does this mean? It means that the signal doesn't get revealed, inventory doesn't get revealed, but a linear combination of them does. OK, I'll skip the other properties. We have a lot of extra work to do, but I'll just conclude there.
OK, thank you, Ryan.